All right, let's see. That'll work. All right, let's see, are you Georgia or Bulldog? I think Georgia. Great. Israel. Yeah, Israel. I'll be Georgia. Okay. Carlos. Let's see. Which one is Israel? I'd say the last. Last name. Good. Good. Okay, can people hear me out there?
Yes.
Good? Okay, great, thanks. So this is seven, right? October 7th. Okay, yeah. All right, great. Okay, so we should probably start. If you would like to come in and pick up your exams, you're free to do so. I'll bring them up until next Wednesday. And then after that time, if you hadn't picked up your exam yet, just send me an email so I can give it to you during class time after next Wednesday. So, okay. All right, so last time we were talking about the LDU decomposition. So let me review a little bit. So we're looking at LDU decompositions. Okay. All right, so the story starts out as follows. So you take A to be an M by N matrix. Okay. And so the first step in the LDU decomposition is to get the lower triangular matrix first. So what we do is we use Gaussian elimination to get the lower triangular matrix. So L is a lower triangular. Okay. And what we do is during Gaussian elimination, we keep track of the row reductions and the elementary matrices associated with the row reductions. And then we use the multipliers in order to construct the L. And then after that, U is an upper echelon form. And so it's going to have certain entries, which are the pivots. And so we can sort of make a diagonal matrix using the pivots. So U can be factored as D times U, where U is, I think it's called reduced upper echelon. So the pivots are going to be ones. Right? So then finally, A will be equal to L D U. Okay. Now, this is assuming that you don't have any row exchanges. So this is okay if one does not need row exchanges. Okay. So if you actually do need row exchanges, then what you have to do is you have to multiply by permutation matrix. So if row exchanges are needed, then what we can do is we can look at P times A. Okay. So then when you do row exchanges, you can actually do or perform Gaussian elimination. And then P times A is going to be LDU, where P is the permutation matrix. Okay. So no matter what, we can actually factor matrix in LDU form, even with row exchanges. But in the case when we do need row exchanges, we have to multiply first by permutation. Okay. Any questions on this? Okay. So let's do an example. So this is an example just to make sure. Okay, so find the LDU decomposition of the matrix A, and the matrix A is going to look like 1, 0, 1, 2, 2, 2. So this is 0 here. Okay. And 3, 4, 5. Okay. All right. So what we're going to do is we're going to perform Gaussian elimination on this A. But when we actually perform Gaussian elimination, what we'll do is we'll keep track of the row reductions at each stage using the elementary matrices. All right. So the first thing we want to do is we want to knock out. So we want to use the 1 as a pivot, and we want to knock out the 2 and the 3. So the first step is to take to keep the first row the same and multiply minus 2 times the first row plus the second row and put it in the second row. Okay. So what do we get here? 0. Okay. Go ahead. 2. 2. Go ahead. 0. 0. Okay. And in the process of doing this, we're multiplying the matrix A on the left by an elementary matrix that has 1s down the diagonal. And it has a non-zero entry in the off-diagonal spot in just one place. So, so where do we actually put, or what entry do we put in this matrix? Okay, and we put it in the 2, 1 position. All right, everyone okay with that so far? And of course, we keep the third row the same. Okay. So this matrix that we have obtained is E21 times A. Oh, let's just put that down. This is E21 times A. Everyone all right with that? Why is it E21? Oh, because the multiplier is in the 2, 1 position. Okay. All right. It has zeros everywhere else outside the diagonal, has 1s down the diagonal, has zeros everywhere except in the position that you specify with the subscripts. Okay, so now what we're going to do is we're going to take this matrix here, and we're going to multiply the first row by minus 3, and we're going to add it to the third row, and then we're going to put the result in the third row. So 1, 0, 1, 0, 2, 0, and then what's the bottom row? 0. Next one is what?
4.
Okay, next one?
2.
2. And what multiplier do we have to use here? What's the subscript?
E3, 2.
Sorry? How about
E31. Thank you. Okay, so let's look at what we do. 1, 1, 1. Okay, the zeros. We're going to put what in the 3, 1 spot?
-3.
Okay, so that's -3 here and 0 there. So notice that when you take the dot product of -3, 1, 0 with this matrix, 1, 0, 1, 0, 2, 0, 2, then, sorry, the top matrix here, 1, 0, 1, 0, 2, 0, 3, 4, 5, you get the matrix over here. So this is E3, 3, 1, E3, 2, 1. Okay. All right, so we just have one more to do. So what do we do next? Anyone?
You do the second row times -2.
Good,
And so it'll be E32 now.
good. So E32, 1, 1, 1, 0, 0, 0, 0. What do we put in the 3, 2 spot?
It'll be -2.
Sorry, did I do this right? Yeah, -2. Yeah, looks good. And so let me kind of move this over slightly so that I have more room to write the matrices. 1, 0, 1, 0, 2, 0, 0, 0, and 2, right? Okay, so this is going to be E32, E21, oops, E31, E21, A. Okay, everyone all right with that so far? Okay, so great. Now this is going to be U prime. Okay, it's in reduced it's in echelon form, and this is going to be here L inverse, right? So how do we find L? Lower triangular, what do we do?
You put all the, whenever we put like E3, like the position 3, 1, 2, 1, 3, 2,
Yes.
you put that all into a matrix into its like respective spots. So in the 3, 2 spot is going to be -2, and 3, 1 is going to be -3, and 2, 1 is going to be
Negative or positive?
positive.
Positive. Okay, so remember, look at negatives of the multipliers. So 2, 3, 2. Good. Okay. Everyone all right with that? Nice. Nice, easy formula for the inverse, right? So A here is going to be L times U prime. And now all we have to do is we have to just factor U prime. So what diagonal matrix do we take? 1, 2, 2. Okay, so that's my D. And then I just divide each row by the diagonal things, right? 1, 0, 1, 0, 1, 0, and 0, 0, 1. And that is my D. Okay. So if we want to write everything out, the answer, so A is going to be 1, 1, 1. With multipliers 2, 3, 2. The diagonal matrix, so this is my L, and then 1, 2, 2. That's going to be my D, and the U, it's going to be 1, 0, 1, 0, 1, 0, 0, 0, 1. That's the U. Okay, any questions on how we did this? That's very algorithmic, right? And we also know we've done Gaussian elimination like a zillion times now. And so you can just keep track of things just by using these elementary matrices. Okay, questions? All right.
I have a question, but it could be looking ahead a bit much. I was just wondering if the diagonal matrix that we wrote down, is that a diagonal matrix of the eigenvalues of A?
No, not necessarily.
Okay. Okay, just wanted to clarify.
Yeah, it's a good question. So later on, you know, how do I say this? Okay, so there are invertible matrices which are not diagonalizable. Okay, so we kind of have to be careful with that. So later on, we will actually be able to put something in diagonal form as long as it's diagonalizable. And when we do that with the eigenvalues, then, when we do that process, then the diagonal matrix that we have will actually be have the eigenvalues on the side. Okay, so this process is a little bit different.
Okay.
I have a quick question.
Yeah.
As well. Can you explain how we got the L matrix again?
Oh, so L turns out to be the inverse of, L is going to be equal to this matrix inverse. So it's E32, E31, and E21, and I have to take the inverse of the whole thing. Okay, so that's how we get the inverse. We get L.
Okay.
You have to move it over to the other side. So. And it turns out that the computation of L inverse is not so bad. I mean, it's actually just getting the multipliers out. Turns out to be quite nice. Okay, other questions? All right. Okay, good. All right, so now what we're going to do is we're going to switch gears a little bit. And so the next topic we're going to talk about are subspaces of Rn, the vector space Rn. Okay. So remember what Rn was. So Rn is the n tuples. So it's a set of all x1, x2 up to xn, where all the xj's are in the real numbers. Okay. And we know that we can add vectors and we can multiply them by scalars. So we have two operations. We have vector addition, and we have scalar multiplication. Now, whenever you have a sub object in mathematics, it could be a subgroup or subspace or sub whatever, you want to have a subset of Rn. So subset of the set. And then you want to make sure that it's closed under the operations. So that's the natural definition for subspace. So definition. A subspace W of Rn is a subset of Rn such that, well, several things happen. So this first condition is actually extraneous, but let's keep it in any way. So it just reminds us about a certain property of subspaces. So the first thing is that the zero vector has to be inside of W. Okay, so if the zero vector is not in W, then it's not a subspace. 2. Well, I put up two operations over here, vector addition and scalar multiplication. So if I take one vector in W and another vector in W, their sum has to be in W too. So if, let's say U and V are vectors in W, then their sum has to be in W also. Okay, so it's closed under vector addition. And then it's also closed under scalar multiplication. So if lambda is a real number, and let's say U is in W, then if I take lambda times U, that's also in W also. Okay. All right, so let me draw some pictures. All right, so first of all, let's kind of draw things in three-dimensional space. So let me kind of write in green there. So, write in green. Try it again. All right. Okay, so let me just draw a picture of a subset inside of R3. So let's say I take a plane here. Okay. And let's say it contains the origin, like that. Okay. So this is W over here. And we know W is a subset of Rn. Does it contain the origin? Yes. And if I take two vectors on that plane, if I add them together, it's on that plane. And if I take a vector on this plane, if I multiply by scalar, it's on this plane too. So this is the subspace. Okay. So in R3, the way you should kind of think about subspaces are they're either planes or lines through the origin. Okay. Or you can get the whole space on R3. All right. So let me do another example on R3. So this time, let me take a line, which is like way up here. It could be parallel, let's say, to one of the axes. Okay. Now, this looks like a subspace because if I just take a vector and I kind of scale it, then it's going to be on there. But the problem is that 0 is not inside of here. So this is W, and 0 is not inside of W, and this is not a subspace. Okay. All right, so let me give you another example. Okay, so let's pretend I'm looking at this sort of parabola, and it's sort of this parabolic sort of bowl, which is actually going down. Well, there are a couple of problems with this. First of all, it doesn't contain 0. And if I take two vectors which are on this parabola, this paraboloid, then if I take the sum of them, then they not stay on the parabola. So this is again not a subspace. Let me change over to this. This is not a subspace. Okay. Okay, any questions on this? All right. Okay, so let me do some examples. so first of all, if I take just the set containing the zero vector, this is a subspace of Rn. So if I just take the origin, for example, then I'm okay. 0 plus 0 is 0, lambda times 0 is 0, everything's good. Okay? And so that's example 1. Example 2, if I take the whole space, this is a subspace. Okay, kind of in a trivial way. And we've actually seen examples of other subspaces. So can someone tell me another example of a subspace? So let's say I have a collection of vectors. Span. Okay, so 3, let V1, V2, up to Vt be a set of vectors, let's say in Rn, okay? And W, let's say I take all linear combinations of these vectors, okay? So this is equal to things of the form C1 V1 plus C2 V2 plus CT VT, where the coefficients are in the real. Okay? All right, so let's just kind of think through why this is a subspace. So is the zero vector inside of W?
Yes.
Just let all C be zero. That's good. If I take a vector which is a linear combination of these vectors, I take another vector which is a linear combination. Is a sum of linear combination. Okay. Just sum the coefficients, right? And then if I take lambda times a linear combination, then do I get a linear combination of that? Okay, so this is a subspace. So this is a subspace of Rn. Okay? And in fact, W, which is the span of V1 up to Vt, is actually the smallest subspace containing the vectors V1, V2, up to Vt. Okay, so there's no smaller subspace which actually contains these vectors. Okay, any questions on this? All right. Okay, so the next thing we want to think about is, these subspaces. Well, maybe they actually are generated as spans of vectors. So the answer is that's going to be true. So what subspaces are going to look like are like planes and lines and sort of three-dimensional sort of linear things which go through the origin. Okay, so that's kind of the way you should view subspaces. So first of all, since we can sort of express a subspace as a span of something, then what we want to do is we want to make a definition to sort of see what the size of this subspace is. Okay, so I need to introduce the concept of a basis. All right. So definition. Okay, so let W be a subspace of Rn. Okay. So a set of vectors V1 up to Vt is a basis for W if and only if, well, let me just kind of draw you a picture. Okay, so there's a picture you should think about on the side. So I have this like plane over here. And so I want to take a vector here, let's say it's V1, and then here's another vector V2 over here. Okay?
So what properties does V1 and V2 have?
Which sort of allows to describe the subspace W. Anyone? So what properties do you think we need for basis? I'm asking. Sorry, someone said it? Yeah, so first of all, we want the vectors to be linearly independent. So 1, V1, V2, up to VT are linearly independent.
So, if we threw another vector in there, they would be linearly dependent. And we really don't need that additional vector to describe that.
All right. One more property.
So what else do you think we need?
W's in the span vector.
How about W equal to the span of the vector?
Okay, so the vector span W. So W is equal to the span of V1 up to V2.
Okay, so we want the vectors to generate all of W. But what we want to do is we want to make sure that we don't have any redundancies. Okay? So in some ways, you have these two ideas of linear independence and spanning. They're sort of pulling against each other in opposite directions. And the basis is sort of the point at which you kind of balance the two out. And later on, we'll actually explain that in more detail. Okay, any questions on this concept? No. All right.
How about some examples? Okay.
All right, so can anyone give me a basis for Rn? Not Rn, no, Rn.
So I'm going to let my W to be equal to Rn. And I want you to tell me a basis for Rn. I think this was on the midterm problem. Maybe the Bulldogs have an advantage over the Georgians. Anyone? Well, 0 has to be in the subspace, but can you give me so you look at the definition of basis, can you give me a set of vectors which are going to generate Rn and be linearly independent? How about for Rn?
The identity matrix.
Okay, so you take the identity matrix, why don't you just pull off the vectors in the identity matrix?
Yeah.
Right?
So that's what you want to do. So you let Ej be equal to the unit vector, right? So it's 1 everywhere, and then so it's 0 everywhere, and then this is in the jth spot. Okay? So if you take E1, E2, up to En, it's the basis for Rn. Okay, so in particular, if you take R3, a basis is 1, 0, 0, 0, 1, 0 is the answer to one of our midterm problems. 0, 0, 1.
Okay. And you can see how it works for like R4 and R5 and R, a million. Okay? Same idea. Okay, and you could, just prove linear independence really easily because you can look at the homogeneous system where you take the identity matrix times x equals 0, all right? Ax equals 0 in this case. And then you can see that all the pivots are there, so it's going to be onto. So it spans all of Rn, and so that's it. You're done. Any questions on this? Okay. So here's another example. So this isn't the only basis for space. So if you take the vectors 1, 2, and the vector 2, 1, okay. So you can use Gaussian elimination and show that these are linearly independent, and you can show that they span R2. So this is a basis for R2. Okay. All right, questions on this? No? Okay. All right. All right, so next I have this, this is sort of a beautiful fact. Once you make the definition, we might prove this later on. So let W be a subspace of Rn. Okay? And so if I take one basis for W and another basis for W, they may not be the same. So look at example 2. I have a basis for R2, but I know another basis for R2 is 1, 0, 0, 1. Right? But what can we say about these two bases? Something even cruder than equivalent. All right, let me give you another example. So if I take 1, 0, 2, 1, it's also a basis for R2. If I take 1, 2, 2, 1, 3, 4, it's not a basis.
They're like, I don't know what it's called. There's like something like the other one. Is it in? Not in.
No. I'm just thinking of something even more basic than that. How many elements does this have? Okay.
Oh, is it if the elements of the set equal the head?
Well, it's the number of elements are the same. Okay. So if you have two bases, they have the same number of elements. So nice statement. Any two bases of W have the same number of vectors or elements. Okay. So let me say, for example, let's see, 1, 2, 2, 1, and let's see, 1, 0, and 0, 1. These are both bases for R2. Okay, so they have the same number of elements. All right, now this is good because I can define the concept of dimension.
And the way I can define dimension is I could just take the number of elements in the basis. So the dimension of W of the subspace W equals the number of elements in a basis for W. Okay, and it doesn't matter what basis you take. You take any old basis you want. And then you just count the number of elements, and that's the dimension. Okay? Any questions on this? All right. Now, what I'm going to do next is I'm going to actually introduce two different subspaces. One is called the column space. The other one is called the null space. And then later on, I'll actually show you how to keep bases for these spaces, probably on Friday. So these are specific subspaces of Rn. All right, so the first one is called the column space. All right, so here's how this story goes. So what you do is you take A, and this is an n by n matrix. And then you're just going to look at the columns of A. So let's enumerate them. B1, B2, B sub n. Okay, there are n columns. Right? Now, just because you have n vectors, that doesn't mean they're linearly independent. Right? So I can still look at the span of the columns and ask what a basis is for the column space. So the column space of A is equal to the span of the columns of this matrix. Okay. All right, so let's do an example. A is going to be equal to 1, 2, 4, 6, 7, 8, 9, 10, 11. Ooh, that's kind of weird. 11, 12, 13. Okay, so not what you would expect. All right. So let's look at the column space of A. So the column space of A, it's a span of the columns. Okay, so let's just write out the columns. So what are the columns going to be?
1, 2, 4,
Very good.
6, 7, 8,
Good.
9, 10, 11,
Okay.
11, 12, 13.
All right. Pretty easy. All right, so then what we want to do is, there could be, these may not be linearly independent. In fact, we know they probably aren't because, you have, this is an R3, right? You have 4 vectors in R3. So it's not going to be linearly independent. So we just want to be able to find a basis for that. And we know that the column space, because it's a span, is a subspace of, well, okay, R3 in this case, but in general, Rn. Right, because the tuples lie inside of Rn. All right, so the other subspace I want to define, you've seen this before in a different guise, but it's a null space of A.
So the null space of A are just the homogeneous solutions of AX equals 0.
So the null space of A is a set of vectors in Rn, this is an n over here, such that AX is equal to 0. Okay, so this is the set of homogeneous solutions. Okay. All right, so let's see if this is a subspace. So I take the 0 vector, let's call this W. Is the 0 vector inside of the null space or not? Okay, that's good because A times 0 is 0. Good. And if I take X and Y in the null space of A. So what does that mean? That means that AX is equal to 0 and AY is equal to 0. Yeah. So that means that A times X plus Y also equals 0. Okay, so if I take two vectors in the null space, the sum has to be in the null space too. Okay, so it's a nice easy check. And then finally, if I take lambda and I take an X inside the null space, so lambda is a real number, then I know that AX is equal to 0, which implies that lambda times AX is 0. And I can move the lambda all the way through. So A times lambda X has to be 0, and that means that lambda times X is in the null space. Okay, so this is property 1, property 2, property 3. Okay, so hence the null space of A is a subspace of, well, R what? Rn. Very good. Okay, great. So, so next time, I'll leave you with a little cliffhanger. We will see how to construct or find bases for the column space of A and the null space of A. Okay, so we'll do that on the next class. Let me ask any questions. Yes? No? Okay, great. So we will see you on Friday. All right, so people have